can be obtained by cyclically commuting these p's and conjugating by an element in the amalgam. So these are the three cases we can, given any two, G and G prime, then we can determine whether or not these two things, elements are conjugate, using this theorem. So what it says is that in our case, we're going to also have to use, again, the construction depends on Gilbert's theorem, Magnus's theorem, and the solution for the generalized word problem for free groups. So it says this, what's the generalized word problem? Given a finite set U of a finitely generated free group, there is an algorithm that decides whether or not elements in F are in the subgroup generated by U. Okay? And then there is this further proposition that says that given a finite set, a subset of a free group, there is an algorithm that decides whether or not there exist integers I and j, such that U to the I, or U to the j, G1, U to the I, is equal to G2. Holds in F, and if they do, the algorithm finds these I and j's. So we're going to have to use these two things, whether or not the element is in the subgroup generated by U, and whether or not we can write elements in the set in this unique way. Okay? So if we put H to be the subgroup generated, for example, U generated by U and G1, and if U and G1 do not commute, in our case we know they do not commute, because U generalized is a centralizer, U do not commute with anything outside that. So H is free on U and G1. Okay? So by proposition 2 we can decide if an element lies in H, yes, and if it does, by proposition 3, get an explicit expression for it, a unique expression for it, because it's in the free group. So one can check whether or not, say, G2 lies in H, and if it does, we can find a unique expression for that, G2. Questions there?
Are you assuming residual freeness somewhere here?
No.
Okay.
I mean,
but this is in that free group.
But the fact that G is residually free is a result of this.
Okay.
That the group, we show that it was residually free, but at the beginning it wasn't.
Okay.
But the first theorem
so
that
it
we
moved on to the,
right.
to the free group.
Okay, so here, so for the group in theorem 2 combined with theorem 3, proposition 2 and 3 above, we'll prove the following, that there exists an algorithm that decides whether or not two elements G and G1 in the generalized free product are conjugate. So what do we do? Again, just to remind you, G is this group, F is free on X and Y, A is a free abelian group, and the cyclic amalgam H is the subgroup generated by the element in the free group U. Now, that generates its own centralizer. So we'll use 1, 2, and 3 in theorem 3 as a blueprint to derive this algorithm. So let G be, again what it says, let G be a cyclically reduced element of G. If G is conjugate to an element H in H, this notation, then G is in one of the factors, and there's a sequence in H and G is in G, such that consecutive terms in the sequence are conjugate in a factor. So if G is conjugate to G is conjugate to H, then G is either in, remember the factors, the free group and the free abelian. So now H is in both F and A, because that's the amalgam. So we can decide whether or not two elements are conjugate in F, and we can decide whether or not two elements are conjugate in A, in the free abelian group. So that's what part A says, yes? So two elements are conjugate in F, if and only if one is a cyclic permutation of the other. And two elements are conjugate. So to know this, what do? We can just check, right? By just writing the words, the elements out in words, represented element, and then checking to see, comparing them to this unique expression that we found before, the U to the I, G1, U to the J is equal to, say, G2. So if it falls in the subgroup, we must also have a unique expression of this form. So on the other hand, two elements are conjugated in A if and only if they are equal, right, in the free abelian group. So we can decide if both elements G and G prime are in F, we can decide conjugacy. If both elements G and G1 prime is in A, we can decide conjugacy. The toughest one is when both P's are in separate parts, in A and in F and in A. So, so the addition can be accomplished. Again, part 2 is just reduced to 1. It says if G is conjugate to an element G prime in one of the factors, but not in the conjugate of H, then G and G prime are in the same factor and conjugate in that factor. So again, we know when they are conjugate in F, we know when they are conjugate in A. So again, that part is also reduced to part 1. So the most interesting part is part 3. If G is conjugate to an element P, P1 to PR. Yes, again, the P1 could be in F, P2 in A, P3 in F, P4 in A, etc. Alternating factors. Then this group G can be obtained by just, again, Magnus says, cyclically commuting the P's and then conjugating by an element of H. And if that occurred, then G is conjugate to P. So for each cyclic permutation, we argue as follows. If G is conjugate to P, written this way, then, and G is an element of F, the first factor, and G2 is an element of A, then due to the uniqueness of the normal form, we have the first part, G1, can be written as P1 times H, yes? So what we can do is replace G1 by P1 H1, and then this element will be conjugated to this, so we can cancel P1 here, and we'll end up with a shorter word. So anytime we do that, we will see that both elements would be of the same length. Okay? So we could continue this in this manner. So what this tells you that for any element, we can generalize this. So we'll have GR is equal to HR inverse, or HR minus 1 inverse times PR HR for R greater than 1 to K as well. So by part 3, if they are conjugate, then there is this in A such that one of these hold, yes, by cyclically commuting the P's and conjugating by H. That's what Magnus' theorem says. So the key interesting thing is here. For example, if we choose number 1, we can put in pinches, and this is where the trick comes in. That we can put in pinch H, H1, where H is some element of U to the I, right? That's part of the amalgam. And we'll see that this here is very important, because if there was some other U to the J or U to the I, and J and I was different, we couldn't use this property, because we'll have some kind of element in there, and that will obstruct the flow of the H and the P1, P2. So the key here is, in doing it, is that we can rely on solving the generalized word problem for the subgroup generated by U and P1, right, in each of these. So we're going to look at to see if G1 lies in the subgroup generated by P1 and some element of the amalgam U. So utilizing proposition 2 to detect whether or not each element in this falls in the associative subgroup. So we can check, because of the solution to the generalized word problem, if G1 lies in the subgroup generated by U and P1. Is G2 lies in the subgroup generated by U1, P2, etc. And once we do that, if it does lie in the subgroup generated by these, then we can get a unique expression for it in terms of the generators, yes? Just as before. So the trick was doing it this way.
The only three group theory relies on
Yes.
all the time.
So due to the normal form for the generalized free product, and by proposition 3, for the existence of some H to have this property, we'll have to have H belongs to U to the I and nothing else, because if it's not that, the problem collapses. We can't find it. And also, we have this expression, u to the negative I, p1 u to the I is g1 for some I. So, and of course, g1 must belong to the subgroup generated by u and p1, yes? So we can check, for example, if g1 lies in the subgroup generated by u and p1, and then we can get a unique expression for it. Okay, so notice that the p1 that I choose, notice u is in the free group, and p1, I said, belongs to the first factor, the free group. So again, the subgroup generated by some word in the subgroup generated by u and p1 is in F. Now if I then choose p2, the subgroup generated by u and p2 is in A. Right? Because p2 is in the free abelian group. Again, we could also solve the word problem for that as well. So these are kind of carefully chosen in certain way. So we can keep on doing this. So if G2 lies, so notice we just pick in the first permutation. Yes? We try to see if G1 lies in the subgroup generated by U and P1. If it does, we can check if G2 lies in the subgroup generated by U and P2. And we can keep on checking until we reach to pk, right? Because we have R goes from 1 to k in the first permutation. So we could keeping the same permutation 1. We could check whether or not the GIs lie in their respective subgroups. And we could also check whether or not we have unique expression for these up to 1 to k for the same I. So if we do get this expression and the GK lies in the subgroup generated by U and PK, then we say that P is conjugate to Q, or P is conjugate to G. This is supposed to be G, sorry. So you see exactly what is going on. So we check in each part, we check in to see if G1 lies in the subgroup generated by U and P1. If it does, check the second piece of the word. G2 lies in the subgroup generated by U and P2. So again, we can get a unique expression, some power H inverse times P1, because we're going to get cancellation by putting in all the pinches. So this is, again, is very nicely done. And so we can repeat the process from 1 to k. So any one of these, if any one of these permutation it holds, as in case 1, then we say that G is conjugate to P. So we test for 1. If it doesn't work, we go to the other one. We test again. If it works for any one of these, permutation, all through going from P1 to PK, then P1 to PR, then we say that G is conjugate to P. Now, if it doesn't, then what happens? So returning to the first case. If G1 does not lie in the subgroup generated by U and P1, then we go to case 2. Because, of course, that one would show that they are not conjugate, yes, because it has to be. So we go to the second permutation and we repeat the process. So if we continue on this sequential pattern from 1 to R, and there is, if for any reason, there is the GK does not lie in any one of these, or the I's are not the same, because notice that the I can change, right? So if we go from, if for any of these, 1 to R, the GK does not belong to the subgroup for any of the permutation from 1 to R, or I is not the same as before. Remember, we want I to be the same because we want to put the pinches together. So if for, say, G1, we have G to the 5, and if for G2, we have U to the 6, then that's a problem here. We wouldn't get the cancellation. We wouldn't get the nice pinch that we need. Yes? So we could rely on the fact that if the I's are different for the same permutation, or if the group subgroup generated by the GK is not in the same, not belong to the subgroup generated by U and PK, then for any of these factors, then we can say that G is not conjugate to P. So you see, so again, to wrap this up, if G1 belongs to the subgroup generated by U1P1, if